Good morning, students. Today our class is about electric field lines properties. So, electric field lines. Okay. So, electric field lines means these are the imaginary lines which are used to represent the electric field. Okay. So, to get the strength, how much strength we are getting by the electric field and what is the representation of the electric field that can be given by these lines. Okay. So, these are the imaginary lines. Imaginary lines. Okay. So, here electric field is the real one because electric field is the real. So, that means real means it can applies the force, and it can create the motion, in a body. Okay, so that's why electric field is real one, but electric field lines are the imaginary lines. That means these field lines which are used to represent the electric field. Okay, so here already we know that electric field is a vector quantity, so that means it has some magnitude and direction. Okay, so in the before classes already we learnt about the magnitude. So that magnitude must be E is equals to what? Force by Q. Okay, so this is the magnitude which is given by the force, that is the electric field. Okay, so here we have to get the direction. So the direction of the electric field and the strength of the electric field and the character and the properties of the electric field are represented by the some lines. That lines are the electric field lines. Okay, so these are the imaginary lines only we are assuming, but they are not exist in real case. We are assuming those lines only. Okay, so that means here these are the imaginary lines which are the representation of the, that means representing the electric field. Okay, so that means here we are taking some more graphs or anything. If you are writing the anything here, so that means we are writing the book. Okay, so book means it is the name which represents the book characteristics. Okay, but not it is the real book. Okay, so this is the name which represents the that characteristics of a book. Okay, so that means here these are the lines which are representing the electric field, but these are not the real lines. Okay, these are the imaginary lines. Okay, now here we have to know the how the electric field is related to the charge, and how these lines are related to the charge and the field and the force. Okay, so now here we have to get some clarification of the direction of the electric field. Okay, so now here we are having electric field properties which is done by the electric field lines. Okay, now whenever we place the positive charge here, the first point is whenever we place the positive charge, then the electric field lines always directed away from, they are radially away from the charge. ఓకే, మనం ఇక్కడ పాజిటివ్ ఛార్జ్ పెడితే ఎలక్ట్రిక్ ఫీల్డ్ లైన్ అన్నీ బయటకు వెళ్ళిపోతాయి. అదే ఒకవేళ నెగటివ్ ఛార్జ్ పెట్టినాం అనుకోండి, ఆల్వేస్ ద ఎలక్ట్రిక్ ఫీల్డ్ లైన్స్ ఆర్ ఆల్వేస్ towards the charge. That means they are radially inward. Okay, if it is a positive charge, the electric field lines are radially outward. Okay, so if it is a negative charge, the electric field lines are radially inward. Okay, so first the electric field lines starts from the positive charge and terminated at the negative charge. If it is a positive charge and the electric field line started here and they are terminated at the negative charge. Okay, so that means electric field lines started at positive charge and terminated at negative charge. Okay, so that's why here this is the starting point, and here after some time they are terminated at the negative charge. Okay, so that's why at the negative charge the field lines are inward, and at the positive charge the field lines are outward direction. Okay, now here they do not form any closed loops. Okay, so these are the discontinuous, not magnetic field lines are a continuous lines. Okay, but the electric field lines are discontinuous lines. Electric field lines are discontinuous. They do not form closed loop. They do not form closed loops. They do not form closed loops. Closed loops means if it will come, if here is a positive charge, it started here, and it is a negative charge, it will be terminated here. Okay, so again they will not start from here. Okay, so they will not start from here, because the negative charge, always the electric field lines are inward. Okay, if the electric field started from here, that means the electric field line will be outward. Okay, so that's why they do not form closed loop. If they do form, if they do form అంటే ఇక్కడ నుంచి ఇక్కడికి వచ్చిన తర్వాత ఇక్కడ నుంచి మళ్ళీ ఇటు వచ్చింది అంటే క్లోజ్ లూప్ ఫామ్ చేసినట్టు. కానీ ఇక్కడ నుండి రాలేదు, ఎందుకంటే మనకి ఇక్కడ నెగిటివ్ ఛార్జ్ దగ్గర ఆల్వేస్ ద ఎలక్ట్రిక్ ఫీల్డ్ లైన్స్ ఆర్ inward in the direction. Okay, so that means here at the positive charge, the electric field line will be started here, terminated, and again the electric field line will be started here and terminated here, and started here, terminated here. Okay, like that. Okay, that's why they do not form any closed loops. They are the discontinuous one. They are not continuous, they are discontinuous, and they do not form closed loop. And the electric field lines always started at the positive charge. They are always started at the positive charge and terminated at the negative charge. Okay, so at the positive charge they are radially outward, at the negative charge they are radially inward. Okay, and the next property is we have to get the direction of the direction of electric field. Direction of electric field. Okay, so for the direction of the electric field, so we have to draw tangent. Okay, that is tangent drawn to the tangent for electric field lines. Okay, so then we are getting the direction of direction of electric field. Okay, so that means let us consider here this is a positive charge and here we are having the negative charge. Okay, so now the direction is from positive to negative. Okay, so the line started here, positive to negative, terminated here. Okay, again started here and terminated here. Okay, so this is inward, this is outward for this one. Okay, now here, so this is the, okay, so this is inward and this is outward. Here also this is inward and this is outward. Okay, this is outward and this is inward. Okay, now see here, these are the outward. Okay, these are the inward direction. Okay, see here, so these are the electric field lines which are from positive to negative. Okay, so when we are drawing one tangent to the electric field lines, let us consider here is the charge. Okay, now I want to get the electric field line direction here. Okay, so that's why if here is the charge, we have to draw the tangent. Okay, tangent means this is the tangent. Okay, so this is the tangent. Okay, so this tangent represents the electric field direction. Okay, if this is the if here we want to get the electric field direction, so then we have to draw the tangent here. This is the tangent, so it will give the electric field direction. So if here I want the electric field direction. Okay, so this is the tangent. Okay, so here I want the electric field direction, then we have to draw the tangent. So this is the electric field direction. Okay, so to get the electric field direction, we have to draw the tangent for electric field lines. Okay, so that is given by the electric field lines. Okay, so here the electric field lines gives the direction for the electric field, that is by drawing the tangent at any place on the electric field line. Okay, at any point on the electric field line, if we draw the tangent, then that will represents the direction of the electric field. Okay, and next property is relative strength of the electric field. Okay, relative strength of electric field. Okay, strength of the electric field means here this is a positive charge, so from the positive charge all the electric field lines are directed away from the charge, so that means they are radially outward. These are the electric field lines which are outward direction. So here I am placing a one loop. Okay, so this is the one loop. Here I am placing one loop. Okay, so this loop, okay, through this loop here we are getting the three lines. Okay, for this loop here we are getting the three lines. Okay, now I am placing the loop here, same loop, same this loop, here I am placing the this loop. Okay, so same size loop if I am placed here, here we are getting only one line which is passing through that loop. Okay, so if this loop I am placed here, okay, I am placed here, so then here we are getting the two lines. Okay, so that means here the concentration of the lines, okay, so the concentration of the lines means here we are having the two, here we are having only one, here we are having three. Okay, so this at this place the density of the lines is maximum, that is the concentration of the lines is maximum, so here we are getting the maximum strength of the field. Okay, if you are placing the charge here, another charge here, the force experienced by the charge at this place is greater than this one, because the concentration of the lines at this place is maximum and the concentration of the lines at this place minimum. Okay, so that's why here the electric field lines represents the strength of the electric field. Okay, so that means the concentration, the concentration of electric field lines. Okay, concentration means what? The density of lines. The density of lines gives the strength of the electric field. Strength of the electric field at that point. Fourth property is the lines should not never cross each other. Okay, so E field lines never cross each other. Okay, so that means here this is a positive charge and this is negative charge. Okay, now the line started here and ends here. Okay, and here another line is there and started from the positive charge and ends at the negative charge. Okay, so here there exists intersection point. Okay, so here if there is some, if the two lines are intersect each other, then here to get direction of E, here we have to draw the tangent. This is the E direction and here we have to get the tangent. This is the tangent which is drawn. Okay, so that means here we are getting the two directions for the electric field. Okay, so this is not possible. Okay, so that's why here at the point of intersection, we are getting the two directions for the E. Okay, so at one point we have to get the one direction for the E, but at the point of intersection here we are getting the two directions for the E, so this is not possible. So that's why here never the two electric field lines cross each other. Okay, so that means here the two E field lines never cross each other. Okay, ఒకవేళ క్రాస్ అయితే ఏమవుతుంది, if they do so then there exist two direction of force or the field force, which is not possible. Okay, now another property is okay, so here the line will be started from the positive charge and then ends at the negative charge. Okay, so here this is a positive and this is the negative. No, here the starting point must and should make the 90 degrees with the surface. Okay, so that means here the starting point should be right angle to the positive charge and the ending point also should be right angle to the negative charge. Okay, so here this is the right angle, and this is right angle, this is right angle, this is right angle, and here this is the right angle, and this is the right angle. Okay, so if this makes the 90 degrees with the one, so then only the line should be exist. Okay, so here it makes the 90 degree, and this is also makes the 90 degree. Okay, so here also this is 90 degree. Okay, so that means whenever it makes the 90 degrees with the charge, then only the line should be exist. Okay, so here we have to get the 90 degree. Okay, so if let us consider, here is the charge. Okay, so this is any spherical charge one. Okay, let us consider here is the charge. Okay, so this is the charge and this is the field force. Okay, now here I am placing one charge. Okay, so the electric field direction, let us consider this is the electric field direction of this. Here is the charge and here also charge. This is the spherical charge distribution. Now here is the charge. So this is the electric field direction. Okay, now this electric field direction is 90 degrees. Okay, so it's okay. Okay, now if I am considering that the electric field direction is not right angle to the this one. Okay, let us consider this is the electric field direction. If it is the electric field direction, here there exists some angle between those two, so that is theta. Okay, if there is a angle, so then we are getting the components. Okay, so this is one component and this is also another component. Okay, so as it is a component, so here we are having the that is force what QE cos theta, and here we are getting the what QE sin theta. Okay, so as this is a QE cos theta, so here this charge will move right side or the left side due to these two forces. Okay, so if the electric field line is normal to the surface, then there is no force which is acted left or the right. Okay, if the electric field line is not normal, okay, so then that means it makes some angle with the one. So then this QE cos theta component will always okay, pull the charge right side. Okay, but here the charge is not moving, the charge will be at that place only. So that means here QE cos theta will becomes 0. QE cos theta will become 0 means QE cos theta will become 0 means Q does not equals to 0. Q never be equals to, charge never be equals to 0. Here there exists some charge. If there is a charge, then electric field does not be equals to 0. Then here the cos theta must be is equals to 0. Cos theta must be is equals to 0 means theta is equals to 90 degree. Okay, so that means if there exists 90 degrees between them, then only we are getting the field which is due to the charge will be correct. Okay, so that's why here at the starting, the field starting point will makes the 90 degrees, and ending terminated point also makes the 90 degrees with the negative charge, and starting point also makes the 90 degrees with the positive charge. So that means when the field line starts from surface, when field line starts from the surface, okay, it is right angle to each other. Why? Because the force applied on the test charge. Okay, so here the force is applied on the test charge, and okay, so here if not right angle, if it makes some angle, then the force is applied on the test charge. Due to that force, the charge will move in the right side, but here there is no existence of the motion for that charge. That means QE cos theta will become 0. Okay, so this is about the one. So that means here the line, the field line which always right angle to the positive surface and the negative surface. This is the one property. So that is electric field is always perpendicular to the surface. Okay, so now electric field lines always like stretching string. Okay, so next one is E field lines are like stretched string. Okay, this is also a one property. Electric field lines are like stretched strings. Okay, So that means these field lines will explains the attraction and repulsion between those two charges. Okay, so these field lines always represents the attraction between the charges and the repulsion between the charges. So for the attraction, if you are considering that this is a positive charge and this is a negative charge, the line should be started with the right angle to the surface, and here this is one and this is also a one, and here the line will be always positive to negative. So here inward and this is the outward. Okay, now here as these two are always under the tension, okay, now when the lines are from positive to negative, after some time those two charges always tends to reduce their length. Okay, so that means here always the electric field lines will be trying to reduce its length. Trying to reduce its length means they are attracted towards each other. Okay, so that means here we are getting the force of attraction. Okay, so that is electric field lines reduce their length, reduce their length. So that this explains the force of attraction between them, force of attraction. Okay, so force of repulsion also represented by the electric field lines. Let us consider here is a positive charge and this is a negative charge. Okay, so this positive charge, from this positive charge the field lines are always outward. For this negative charge these field lines are always inward, so these are the inward. Okay, now if the always we know that from the positive to negative, sorry, here we have to take the same charges to represent the repulsion. So as always we know that the field line started at the positive and ended at the negative charge, but here is the positive charge, here is the positive charge. So as this is a positive charge the field lines are outward, these are the outward. Okay, so now see here, as this is the positive charge, so this field lines wants to go nearer to the positive charge, but here as this is a positive charge so it will be repelled by this positive. So here the line will be started here, but due to the repulsion of this positive charge it will be go like this. Okay, so this field lines from this charge also, here we are getting another outward line. So this line also wants to go towards this charge, but due to the repulsion force of the positive charge it will goes like this. Okay, so these two lines are never intersect each other, these two lines are parallel. Okay, as these are parallel, so the force which the force will be always in the transversal force. Okay, so here we are getting transversal force, that means perpendicular force we are getting. Okay, so this line applies the force in this direction, this line applies the force in this direction. Okay, because those two are repulsive each other. Okay, so that's why this line force is in this direction, this line force is in this direction. Here also another line wants to go nearer to this positive charge, but here as it is a positive charge it will repel that line, so that's why it will repel and it will goes like this. Okay, so here also we are getting the another line, but it wants to go nearer to this charge, but due to repulsive force of this force and it will goes and it will moves like this. These two also parallel lines. Okay, so here those two are never intersect each other. If they intersect then there exists the two lines, two directions for the force or the field. As those are the parallel lines, here those two are intersect each other, not, it does not intersect because of the repulsive force between those two also. Here there exists the transversal force in this direction, there exists a transversal force in this direction. Okay, so this represents the repulsive nature of the two positive charges or the two negative charges which is given by the electric field lines. Okay, so here inside we are not getting any line because the first line only the first line from the this positive and this positive get repulsed. So that's why here we are getting electric field is equals to 0. So inside the electric field we are getting 0 in between the two positive charges, but here inside electric field here we are getting the maximum electric field inside the positive and negative charge. Okay, so okay, So, this is about the attraction and repulsion, which is given by the electric field lines. This is the representation of the electric field lines for the attraction, and this is for the repulsion. Okay, so here those two lines are parallel, means those are repulsive. Okay, now here electric field is real one, electric field line is imaginary one. Okay, now here we have to get the shapes from the electric field lines. That means we have to get some shape of the electric field lines. So for the point charge the shape is different, for the line charge the shape is different. Okay, so here we have to get some electric field lines shapes, that is depending on the shape of the charge. Okay, we are having so many type, we are having so many distribution of charge, that is a point charge, line charge, sheet charge. Okay, so by depending on the distribution of charge we are getting the lines, field lines. Okay,